Announced.
Yes, thank you. Okay, well, welcome to the March Howard Astronomical League monthly meeting. It's nice to see you, everybody on. We have an excellent speaker tonight and a nice agenda. So without further ado, I think I'll just go ahead and get started. Can everybody see my screen? Okay, thanks. So our agenda tonight. We'll go around the room and just say hi if anybody wants to say hello, anybody new. And then we'll talk about our what's out in the sky this month. This is kind of a new thing we've been doing. We've been going through lunar, solar, planetary, and whatnot. And in memory of Bob Prokop, the lunar section will be dedicated to him. And then Wayne will talk about his section that he normally does. And then our speaker and some announcements and our normal set of excellent Astro images we'll go through, and people can share their good stuff. So introductions. Is anybody new or a guest that would like to say hello?
Sure. This is Eric Holtzman. I'm a new member. I live in Ellicott City. I'm an electrical engineer at Northrop Grumman. And, I've been to one of your star parties, and I think it was time to just join the group.
Great.
Welcome.
Eric and I are ex-colleagues, by the way.
Hi,
Anybody
this
else?
is Satish. I'm new to this group. I live in Woodstock, just a couple miles away from the HAL weaving site. I'm a software developer, basically developing softwares for a major healthcare provider in Maryland and DC. For a long time now, I have been thinking about pursuing stargazing or observing the celestial bodies out there as a hobby. After much research, I got a telescope now. When I was researching about the viewing sites nearby, then HAL came up first in the Google. Then I learned about the group, and then I found like it's a larger group out there for it existed for like several years now. And then without any second thought, I just signed up for the membership. I'm a beginner using the telescope though, but I'm learning, and I'm looking forward to learn from the experts like you.
That's fantastic, and it's great that you live so close, and I hope we see you. That's what the club is all about, really. Yeah. We like to share and promote the hobby, so that's fantastic.
Yeah.
Also, I want to talk to you about websites at some point, but I'm just kidding.
Yeah, sure. I'm happy to help.
just joking. But we're having a star party this Saturday, so maybe
I'm planning to come over this weekend for the star party. Yeah,
terrific. So we have the members only and the public star parties. The public star parties tend to be more focused on sharing views with the members of the public, but the members only parties are often people debugging equipment, but that's where people really like to share, and that would be a great place to learn. So
okay, got it.
Welcome.
Thank you.
Anybody else? Okay, so I will just move on to the next section here. And so we would like to, we have a ex-president and active club member who passed away recently, and he was just such a terrific human being, and great promoter of the hobby and kind to everybody. And so we thought we would have a tribute, and I see Lisa, his daughter, is here. Welcome. So we would just like to spend a couple of minutes talking about him and sharing some of the the nice stuff that he did. And so Jim Johnson was going to say a couple of words if that's okay with everybody.
Thanks, Victor. The universe lost one of its most dedicated and enthusiastic observers on February 23rd of this year, and HAL lost one of its most strident supporters of public outreach. My my first encounter with Bob came when I attended my first meeting, February of 2012. He was president. And I went into that thinking, this is going to be a bunch of, there's just so much stuff to geek out on, facts about celestial bodies and equipment and stuff like that. But Bob put the human touch on the astronomy that we were doing and on the outreach that we were doing. I saw him again. The next time was at my first public star party, and I set up equipment. He ended up setting up right beside me, and I was just completely blown away all night at the things he was showing me. One of the objects he talks about in one of his books. And then at subsequent star parties, if I went out to Carr's Mill and Bob was there, or Alpha Ridge, if he was usually there ahead of me, I'd knock somebody out of the way to sit up next to him, because that was just like a great ticket to a great star party. He was just so interesting to be around. So I'll close this little piece with asking that you take a second to honor his legacy by reflecting upon how he has influenced you and and inspired your astronomical journey, and to reflect on how you're going to do astronomy going forward, based upon his inspiration. He's worth it and you're worth it. So please do that. Thanks, Victor.
Thank you. Thank you, Jim.
I'd like to add that I had the privilege of serving under Bob as secretary, and he was also a great administrator. I mean, the fact that he was reelected for 3 terms as president of the league tells you that he was getting something right. In fact, he got everything right. And I will miss him. Bob's wife unfortunately passed away some years ago. I hadn't had the pleasure of meeting her, but my wife had, because my wife worked with his wife for a period at NSA. I think it can be said now that Bob was also an NSAer, a very accomplished Russian linguist, and I'll say no more about that.
Thanks, David. I think there's probably not hardly anybody on this call who wouldn't have a lot of nice things to say. I'd like to maybe defer until the end of the meeting. If there's some time, we can all sit around and talk more about Bob. But before we move on with the rest, Lisa, would you like to say anything?
Hi, everyone. Thank you, Victor, for inviting me. And I'm just so honored to be amongst you all. I'm very interested in the talk that's coming up. I just wanted to share with all of you what a light you were in my father's life. He found HAL in one of his darkest periods after my mother died. He said, he could get through the days, but he didn't know what to do with himself at night. And he turned to his hobby of astronomy, and he found you. And you have been a beautiful community. And I can't tell you, how many drawings and photos that he enthusiastically shared with us, his family, from your meetings. He absolutely loved the social events. He put so much energy into picking out cookies and pies when you would all get together in person. And he always made a priority to get to the virtual meetings too. He was a real advocate in our neighborhoods for the public star parties. You can see here that he even hosted some driveway lunar and solar observation sessions for the children in our neighborhood. My son is wearing the the space PJs that you see in this picture, and the little girl you see looking through the scope is now a Mercury fanatic, thanks to my dad's instruction during our pod school year. And so I'm just, so grateful to you all for being such a beautiful community and sharing in your enthusiasm and passion and giving him an outlet to do the same. I just wanted to express my truest gratitude to all of you, and I will leave it there, and I will enjoy the rest of the meeting with all of you. Thank you.
Thank you. All right, let's move on. Again, we can, if we want, after the rest of the presentation, if people want to talk a little more and share some things, then we can spend a little time doing that. Okay, so now with our next section about what's up in space, changing the tone a little bit, let's get back to the stuff that we like to do here. Wayne, thank you for presenting or for preparing this.
So I found this preprint, or actually I found a news article about the Hubble Space Telescope observations that have been, I have identified a possible runaway supermassive black hole. This comes from a preprint by Van Dockum and his co-authors from February of 2023, so it's recent. And the title is a candidate runaway supermassive black hole identified by shocks and star formation in its wake. Now, this is a professional publication, not a news report. So that's why the title is long and a little obtuse. I do want to point out, though, that the paper is a preprint. That means it's still going through the refereeing process. So it's possible that by the time it's actually published in the Astrophysical Journal Letters, that it might change a little bit. So they got this.
Are you refereeing it?
No, no. It's a publicly posted preprint. I see the link didn't show up on your slide. Okay. Oh, well, maybe I added it after I sent it to you. Nope, that's okay. I'll send the link out on the email list, I guess. So they got their Hubble data from the Advanced Camera for Surveys, or ACS, and they saw this funny looking streak on the image, and they went through a lot of effort to make sure it was actually real and not some kind of an artifact, a cosmic ray or some other kind of artifact. And since it showed up on many different images, they concluded it was real. So they didn't know what it was. They've never really seen anything like it. It looks a little different from an astrophysical jet just because of its size relative to the presumably host galaxy. So they obtained Keck 10-meter telescope with the low resolution imaging spectrometer, and they took spectra of the galaxy, which is on the right, located that real bright thing up just above the center, and the streak. And from that spectra, they determined that they were both at a redshift of 0.964, which suggests strongly that they're at the same distance from the sun, from the Milky Way. The spectrum also shows that the galaxy does not have an active galactic nucleus, and that there's, if you look at the image carefully, it shows evidence of a merger or an accretion event about 100 million years ago, judging by the disturbed nature of the disk of the galaxy. Because of the colors along the streak, they determined that the colors actually change, and the change is consistent with an aging stellar population that increases. The age of the stellar population increases as you get further from the far tip of the streak from the galaxy. So the closer you are to the galaxy, the older the stars are. Because the jet shows stellar continuum properties and not a power loss spectrum, they've determined it's not an optical jet like you might get, say, out of M87 or whatever. It's not that kind of a feature. And the characteristics of the gas suggests that the streak consists of ionized gas from fast shocks, physical shocks, and young hot stars, which ionize the circumgalactic medium around the galaxy. They estimate that the supermassive black hole, which is presumably at the tip of the streak, the lower left of the streak, was ejected about 39 million years ago. And this is based on the modeling of the color changes along the streak. In addition, above the galaxy, I've indicated on the with an arrow, there's a possible another object that they have identified as possibly a binary supermassive black hole. If you look at the preprint, there's evidence that there's actually some material, glowing material between that binary supermassive black hole and the galaxy, similar to the streak, but just much fainter. So what they hypothesized happened is the galaxy had a binary supermassive black hole at its center. It has a binary system because of a previous merger with another galaxy with a supermassive black hole. And then there was a second merger event about 100 million years ago that had another supermassive black hole, and the three body interactions between those three supermassive black holes eventually kicked the binary black hole and the ejected black hole out of the system. Okay. So this is a really interesting object. They suspect that if, unless they were just incredibly lucky, these sorts of things might be common. And so they are planning to perform more observations to see if they can find them. And also they're going to try to get some JWST time to examine the ionized streak there and learn more about the system. So I thought this was an interesting.
Yeah, that's a cool one this month.
Interesting observation.
It's nice to see Hubble still doing good stuff.
Oh, Hubble is definitely still doing good stuff.
All right. There's no diffraction spikes. Wait a minute.
Nothing bright enough to see them.
All right. Thanks, Wayne. So without further ado, I think we'll move on to our featured speaker this month. It's Dr. Melissa Trainer from NASA GSFC. And I think I see one of your colleagues, I don't know, you're on my screen, you're both sitting right next to each other. Ernie Wright is his square is right next to yours. So maybe they're both in Greenbelt or something. I don't know. Maybe Zoom is putting you geographically together. Anyways, so Dr. Trainer is from NASA and is a planetary scientist at the Goddard Space Flight Center, who is with expertise in the composition of planetary atmospheres and the production of organic molecules and aerosols via in situ synthesis pathways. Maybe we'll all know what that means after the talk. Dr. Trainer currently serves as the Deputy Principal Investigator for the Dragonfly mission to Saturn's moon Titan, which is part of the NASA Planetary Science New Frontiers program. She's also the lead for the Dragonfly mass spectrometer, which enables investigation of Titan's surface composition and characterization of potential prebiotic chemistry. How cool is that? Welcome, Dr. Trainer.
Yes, thank you so much. I'm really excited to be here presenting to everybody today. So let me get the slides back up. Okay, can everyone see my slides?
I can.
Excellent, great, and I assume everyone's hearing me okay. So again, thank you so much for having me. Today I'm going to talk about the Dragonfly mission. So you kind of get a hint of it with this cover art here. We're going to Titan, which is a moon of Saturn, and we are a rotorcraft. So we call it a rotorcraft lander that is able to actually fly around on the surface of Titan. I'm going to talk about it a lot more though. And let's see. Okay, and then you heard a little bit of a bio, but it was very professionally oriented. I like to just share a little bit more about myself too. So I am a planetary scientist. I've been working at Goddard Space Flight Center. I just passed my 14-year anniversary, so I've been here for longer than I like to realize when I do the math. And as was mentioned, my role on the Dragonfly project is as both a deputy principal investigator, meaning sort of like the deputy to the lead scientist for the mission, who is Dr. Elizabeth Turtle at the Hopkins Applied Physics Lab, so local. And I'm also the lead for one of the instruments that is on the payload. And so that's kind of where my expertise is, and where I focus a lot of my time at the moment. But I came here by way of University of Colorado Boulder, and just some other things that I do professionally. I have pictures across the bottom. I'm also working on the Da Vinci mission, which is a mission to send a probe to Venus. And in kind of a similar role, working on atmospheric composition. And then one of the instruments, I was on the science team for the Mars Curiosity rover, which has now been on Mars for over 10 years, which is amazing, and still going strong. And then in my free time, I enjoy spending time with my family. This picture is a little bit old, but we really love going to national parks. So we've, especially since the pandemic started, we've been like really checking off a lot of national parks on our list and having a good time doing that. And I did just get a new telescope, and I may come join one of your star parties one day. And I'm also looking forward to lugging my telescope to various of these national park locations next time we head out. Before I start talking about this mission and like what we're going to learn and why I'm so excited about it, I always want to pause and just acknowledge the team. So it takes an incredible number of people to make any of these missions happen. This is a photo from a recent team meeting back in November. And this is just a small subset of the team. This is a lot of the science team members, as well as some of the engineers, et cetera. But we've got like, hundreds and hundreds of people that are working on this mission. You certainly can't do without it. This is definitely a team sport exploration.
Hey, I'm sorry to interrupt you. Arjun, I see your hands up.
Oh yeah, I had a question.
Well, actually, before you go, I think in today's meeting, Dr. Trainer was requesting that perhaps we could save our questions for the end. So,
Oh no, I was just gonna say that I think I went to the building last week on Sunday. There's like a girl power event. My sister went there, so I remember that.
Oh, very cool.
awesome.
Yes, it's right next building.
Awesome.
All right. So one of the things that we think about with Titan is that it is really a location in our solar system where we can do some really unique and really compelling science. And I mean, not just compelling from a planetary science perspective, but compelling from like a humanity perspective. That's how I think about it, right? So we do not really know how life came to be on our planet. And right now, Earth life is our data point of one. And that's the only, life that we're aware of right now in the whole universe. And we can't really go back in time in our time machine to try to figure out, well, what was Earth like when life was, coming into being, and what were the conditions and what were some of the processes that were taking place at that time to make it possible. However, we can visit other places in our solar system that might provide some clues to these puzzles, and that's a motivation for going to, for example, Mars or some of the other places in the solar system. But Titan is actually one of the premier targets for this question, especially one particular aspect, and that's because there's a lot of features of Titan, Saturn's moon, and I'm going to kind of walk through a lot of them that make it very Earth-like in a surprising way. It's all the way out by Saturn. It's super far away. It's really cold, right? It's not by the sun. It's made up of some different components than Earth is made up. But actually, the processes that are taking place on Titan are very similar to processes that take place on Earth. And there's some features, especially of the chemical environment on Titan, that we think is really relevant to the processes that could have been happening on Earth billions of years ago, that especially might provide insight to sort of that in situ chemistry synthesis and abiotic chemistry that we were hinting to earlier. But to help address that question, I'm going to explain why. You don't just have to believe me. I'm going to tell you why this is true about Titan. So Titan is really unique in lots of different ways. First of all, here's the family photo of Saturn's moons. It's, the largest by far. See, it really stands out. I just want to point out another moon of Saturn that we think about a lot when we think about, where are places in the solar system we can look for life, is Enceladus. And that's, I don't think it's my pointer, but that's, I think the 6th one or 7th one, then from the left, it's, quite a bit smaller. Titan, is aptly named, right? It's the biggest by far. It's also really unique, not just among the Saturnian satellites, but it's actually really unique among the other moons in our solar system. If you look at this image, I have them labeled. So we've got these in order of size, starting with Ganymede. Jupiter's Ganymede is the biggest, but not by that much. And then going through kind of the Galilean moons, and then some of the other moons that we're all familiar with. And there's one thing that should really stand out about Titan when you look at this picture, right? Every other moon, you can see all of these craters, or you see, these big fault lines like on Europa on its ice crust. You can see the surface, and you can see it directly, impacts and processes that are relevant on the surface, Io's, volcanoes. Titan, right, just looks like a fuzzy ball. And that's because Titan has an atmosphere, and it has a very substantial atmosphere. And it's the only moon in our whole solar system that has an atmosphere. And that's really interesting because, again, that creates an environment that is unique compared to the rest of these moons. This is another one kind of comparing some of the other just planets in our solar system, that have atmospheres or not, that we're frequently exploring. And I like to take this image and kind of reshuffle it and put it in order of surface pressure. So if we're looking at the atmospheres of terrestrial bodies in the solar system, Venus has the densest atmosphere of those by a lot, about 90 bars, so 90 times the Earth's surface pressure. But then actually Titan is next. Titan has a surface pressure that's about 1.5 times that of Earth. And, but, pretty close to that of Earth. But that tells us, right, there's a lot of gases in its atmosphere. We also know that the primary gas in Titan's atmosphere is nitrogen. That should sound familiar. That's the primary gas in Earth's atmosphere, and it's the only other place in the solar system where that is true. So right away, we already have some similarities in what's going on in the atmosphere. So I'm going to orient you a little bit to what it's like to live on Titan, and go through the seasons. So Saturn has axial tilt. It's not that different than what we have at the Earth. So it's about 26.7 degrees. It takes it nearly 30 years to go around the sun. So 30 Earth year, which means, and Titan has the same year. Titan's day is about 16 Earth days. So that's how long it takes it to go around Saturn. And because it has a similar axial tilt, you're going to get similar seasons, just like we do on Earth. And so I have this table here I like to put up again, just to think about what are these timescales like on Saturn with a 30-year year. So for example, when we're looking at where we are now, I kind of marked it with the arrow. The summer solstice was in May of 2017. So it is northern summer, and it will not be northern fall until May of 2025. So we've got these like 7-year-long seasons on Titan. So there will be some similarities in how you react to changing seasons, right? Dictated by the tilt against the sun and where the subsolar point is, but they're going to be really slow, right? Reacting a lot slower than we're used to. Now, how do we know so much about Titan? There certainly are ground-based observations, and there are, orbital telescope observations, but we've also had some close exploration of the Saturn system. And so that's marked up on this plot that starts with kind of Pioneer and Voyager flybys. But then we sent the Cassini-Huygens mission, which was a joint venture of NASA and ESA, quite a while ago, that arrived in the Saturn system in 2004. So you want to start from the right side of the graph in the red region here with the Cassini nominal mission. And then there was also the Huygens probe, which Cassini dropped off into the atmosphere of Titan, and it went down to the surface, making measurements along the way. And then Cassini continued to stay in the Saturn system and have many flybys of Titan to gain information. Now, what this plot is showing is what the Cassini project's timeline looks like plotted against the Saturn year. So again, it's showing up kind of in, after the northern winter solstice and going through, and then we have extended missions for Cassini, which was called the equinox mission because it was right around the vernal equinox. And then it goes into the solstice mission coming up on the northern summer solstice, at which point the Cassini spacecraft was then deliberately crashed into Saturn to put it out of commission. Now, if you look at this timeline, it's a 13-year mission, 13 years that we were in the Saturn system, but not even a full Saturn year, which is kind of like mind-boggling to me. And then another fun fact, which I'll get to, is based on when we expect to arrive at Titan with this next mission, Dragonfly will be right around the same time of year as when the Huygens probe was dropped in January of 2005. One Saturn year later. So Saturn's and Titan's year is so long, it's like on the scale of how long it takes us to like complete a space mission and design and build a new one and launch it and get it back. These are some pictures of Cassini and Huygens. The one on the left shows the Cassini spacecraft, and it's really huge. You want to look in the bottom left corner where there's a desk and a chair to get kind of an idea of scale. Right? This is like a really massive spacecraft. And then on that, kind of gold wrapped spacecraft on the right is the Huygens probe within its own heat shield. And then you can see on the right image with the people in it, you can see that Huygens probe embedded in its heat shield. And the engineers there working on it give you kind of an idea of how big that probe was. And so that probe is sizable, and it's only a small part of what the Cassini spacecraft is in that image. Now, as I mentioned, Cassini was there for about 13 years, and this image shows all of the flybys that Cassini made of Saturn. It was orbiting Saturn, but through the Saturn system. And we also mapped here in this image where the Titan's orbit is, just to give you an idea. And so Cassini in its lifetime did 126 close Titan flybys, and that has provided just a wealth of information about Titan, and including imaging of the surface, which I'm going to show you. So some things we know about Titan, some fun facts here about its diameter, about 5,000 kilometers. Its surface gravity, I want to bring up because that comes up again later. It's got about 14% of the gravity of the Earth's surface, and it's just a little bit, less than at the moon's surface. I mentioned that Titan is extremely cold. So the surface temperature on Titan is 94 Kelvin, which, translates, if you're thinking of like a local weather report, to minus 290 degrees Fahrenheit. So really, really cold, too cold for, you or I to go and hang out. And I also mentioned the surface pressure is 1.5 bar, 1.5 times the pressure surface. These images on the right, I always like to point out. So on the left, we've got this fuzzy image. And it's fuzzy, not just because there's an atmosphere there, but actually because the atmosphere is full of like a planetary haze that is formed in the atmosphere from photochemistry. So it's not that dissimilar than some of the smogs that can form in some of our cities. So you have sunlight coming in, and there's chemicals in the atmosphere that then interact with the sunlight and lead to the production of organic particulates. And then those particulates fill the atmosphere in a way that makes it so you can't see down to the surface just through visible wavelengths. Now, the image on the right shows kind of the first time we got a glimpse of the Titan surface when we finally got there with Cassini. If you look in the right wavelengths, you can see through that haze and you can see the surface. Another thing about Titan, we've got this, I've talked about the surface pressure, but we've also got this very extended atmosphere. And that means this is like a lot taller than the one at Earth. And so on Earth, where you might have your clouds and your stratosphere, troposphere boundary in like the 10 to 20 kilometer range, on Titan, that's going to be a lot higher. Another good comparison is that on Earth, there's no true, top of the atmosphere, but we usually think of the extent of the atmosphere starting to really drop off in the 100-kilometer range, right? And on Titan, it's more like over 1,000. So when we were doing flybys with Cassini around 1,000 kilometers, you could still see all of these molecules that were being formed in the atmosphere. And then finally, the interior of Titan is really interesting. It's got some cool analogs to the structure of the Earth's interior, but with some different materials. So I like this cutaway a lot. It kind of shows you, our concept of what the interior of Titan looks like. So with Earth, where you would have a rock crust, right? Silicate rock crust. And then in the layer below that, in the mantle, you'd have, the liquid rock layer. So at Titan, you have something similar, except that the crust is made of water ice. And then below that water ice crust, you would have a liquid water, mantle around, ultimately, some kind of a rock core. And so you have these layers that are somewhat similar to what we think of as Earth. And then you've got that haze that's formed in the atmosphere. It eventually deposits on the surface. And then you end up with this like dust that you can almost think of, sort of like dirt on the top of that water ice crust. So again, back to this question, why does Titan look the way it does? When we look at it, why is it hazy? And it comes back to this complex organic chemistry. So I mentioned that nitrogen is the primary component in Titan's atmosphere. The next most abundant species is methane. So that's the smallest hydrocarbon molecule. And when the sunlight interacts with these molecules, it leads to this very complex organic chemistry that forms larger and larger hydrocarbon molecules and molecules of nitrogen in them. And as I mentioned, many of them ultimately form particulates. They make that haze, and that haze eventually deposits down to the surface. And this is really key for what we're so interested about Titan, because now you've got this global organic synthesis that could be forming compounds that are relevant for what we think of as important for biochemistry or the chemistry of life as we know it. And it's sort of raining down all over the different surfaces. And even though that's happening in this location where it's, really cold and really different than the environment we probably had on Earth billions of years ago, just understanding, well, how complex does that chemistry get? What kinds of compounds can you get from that? And then once they are on the surface, what further processing can happen? Because as I'll show you, there's some really fascinating environments on the surface. And so because of this, this is really the only place we can go to where this is happening. Something like this might have happened on the Earth billions of years ago. We think there are periods of time in Earth's history where you'd have enough methane in the atmosphere that you could get the same kind of photochemistry and organics kind of raining all down onto the surface. But that's not happening anymore, right? And Titan, we can go there and we can see this process today. So now I'm going to show you some really awesome images of the surface and just talk about some of the very different environments that we have there. Now, before going to Titan with Cassini-Huygens, it wasn't completely clear what kind of surface we might find when we got there. And so, in fact, when they were designing that Huygens probe, you had to factor in considerations, we have this rich organic chemistry. Maybe most of it just makes ethane, and maybe most of that ethane just condenses as like an ocean on the surface. And is it possible that the probe is actually just going to splash down in a global ocean of ethane? Which, that was one of the possibilities. But as soon as we got there and started to get images of the surface, the first thing that really pops out is that this is not just a homogeneous, everything looks the same surface, right? It's not a water world or a hydrocarbon liquid world. You see just all these colors and all these structures tells you there's a lot of diverse environments. So what are some of those things? One, there are these equatorial dune fields. So you can kind of see them around the middle of the image. They are created just like sand dunes on Earth. You have particulate matter. It grows into sizable pieces like a sand, and then wind blows in. Wind blows consistently, in generally one direction, and they all align in certain ways around the wind. And in this image, if it's showing up well enough on your computers, you can even see, just like dunes on Earth, those sand dunes kind of form around these larger landmarks, like these topographically higher locations that are there. And so, this is an extremely Earth-like process that we can study. It's just happening with different materials. Instead of silicate sand, the dunes are made up of these organic particles, maybe organics with a little bit of water ice mixed in, that form these sand particles that form the dunes. We do have impact craters on Titan. You're not going to see as many as on an airless body, but we do have them. Here's an image of one of them in the radar, and you can kind of see in the overall image too as well. When the impact crater is coming in at Titan, it is hitting the water ice crust. And if the impact has enough energy, then in the formation of that crater, you would get a melting of that water ice crust. And that would lead to liquid water on the surface. And if it's a large enough impact and you have enough energy coming in, that melt could be persistent for quite a long time, even hundreds of years. Before it can freeze over, even though it is very cold there. And so now we have a situation where we have these liquid water environments. We've got all this organic material raining down, and now we've got both those things mixing. And we think that is a really important process and kind of environment where you may get some fascinating prebiotic chemistry. We do see evidence of tectonic structures. So places where the crust is, being uplifted. It's not going to be mountains as high as those on Earth, but we do see that on Titan's surface. And then this next one is fun, potential cryovolcanism. And in some places, I think even confirmed cryovolcanism. So these are places where, again, just like on Earth, where you have a volcano and you get, liquid rock from that interior mantle layer coming up and erupting onto the surface. And again, you can imagine, right? We see images of this from Hawaii and other places with impacts. You can have that lava flowing, and it can take quite a while to cool down because it's very hot when it's coming out, even though, obviously it's not hot enough on the Earth's surface to keep the rock liquid. So you can get something very similar to Titan, just again with very cold materials. So in this case, it would be water or possibly water ammonia mixtures from that interior liquid layer, that liquid ocean, and they'd be erupting up through the surface, the ice crust, and then in placing those materials on the surface. And again, it may take some time for those to cool. And that's another environment where we could have liquid water persistent on the surface long enough for some really interesting chemistry to take place once you mix in those organic molecules. Here's another image from above of that site, kind of showing where you can see sort of why we think this is a flow, right? Coming out from one location and flowing down. We also see river channels, especially some really good images that were captured by Huygens on its way down through the atmosphere. So there's periods of methane rain. On Titan, we have a methane cycle that is similar to the water cycle on Earth. You can get, there's not just methane gas in the atmosphere, but you can make clouds and you can have rain and therefore periods of rivers flowing. So we definitely see evidence of that on the surface. And then finally at the poles, especially the North Pole, we have these large polar seas, and those are the really dark areas in the image on the right. And these seas are composed of largely liquid methane and liquid ethane. So I always like to say Titan is the only other place you can go to in the solar system where you could go sailing and on open seas, Earth and Titan, and that's it. And everywhere else, if there's any water, it's inside. Here's some images showing kind of from that methane cycle. We see clouds, we see weather patterns, and there are some great times where we've had evidence of rain falling. You can kind of see an area that looks dry and the cloud comes in, and then the area looks wet and then it looks dry again. So you can see the effect of this methane rain. And then finally, I want to just highlight the Huygens landing site. So after the probe landed, it did survive on the surface for about 70 more minutes. And it took this image, the orangish image that you see over here from the surface. And so that gives you a view, where it landed has been classified as like a former floodplain. And there's all of these cobbles in the image, and the image on the right is from the moon landing, and there's a footprint there that kind of, these were aligned to provide scale so that you get an idea of the size of those cobbles. And one question we have is exactly what are those rocks made of, right? So a strong hypothesis is that there are probably water ice that have been rounded in with erosion in the kind of like methane flows that we might have in the rivers and periods on Titan. Maybe they're coated in some organic material, maybe there's some organic material, frozen in the ice. We're not entirely sure. But those are some of the concepts again, but without that knowledge of what that stuff is made of, I could probably trick you and tell you that was a picture from a desert somewhere. All right. So again, just to walk through, one of the reasons we think Titan is so fascinating is that we believe it has the key ingredients necessary for life. These are energy. And so Titan gets this in the form of sunlight, which provides just, solar energy, as well as the photochemistry that takes place in the atmosphere, creates these molecules that go to the surface. And that's actually a way to transmit chemical energy as well. There is abundant organic material. So, you can't even see the surface because the Titan atmosphere is so full of organic particles, especially at some of the higher altitudes. And so that haze in the atmosphere, we know is comprised of complex organic materials, and it ultimately goes to the surface. And this is really important because, again, as coming from someone who has also worked on the Mars mission, when we're on Mars, we're just like desperately looking for any organics in the surface, right? And at Titan, we just know they're everywhere. It's just everywhere. This is like an organic molecule factory. And so what we're interested in here is understanding what are those materials and how might they be transformed on the surface. And again, there's liquids. So water is the solvent that is relevant for biochemistry as we know it. And there's water available in the interior, but we can see evidence on the surface that there has been water available in the surface in Titan's past, particularly in the form of these impact environments. But we also know there's a second liquid there. There's this active methane cycle. You have these methane, ethane lakes and seas. And it's possible, this is really intriguing, kind of going the next step is that an environment that could perhaps support a biochemistry for life? We don't know it. And so that makes it that's a whole other level of thinking about Titan that's really exciting. So again, this is something at Titan alone where we can really study this kind of chemistry, this process happening on a planetary scale, and in a way that might give us a window into things that could have been happening on Earth's past. So this helps, it's the next step towards answering some of these fundamental questions. What makes a planet or moon habitable? What chemical processes can lead us to the development of life? And then the big question, which we're not going to answer with this next mission, but this is all just part of this big question that we all have in planetary science and NASA exploration is there life somewhere else? Can we either find life or understand what does it take for that kind of chemistry to develop in a way that then when we look out to all these other environments, that we can identify places where this could potentially be happening. All right, so to do that, we're with this next mission to Titan to explore this fascinating place and just start to answer some of those questions. We have a mission where we're going to be able to visit multiple places on the surface. So as I mentioned, with the Cassini mission, I showed you a bunch of images. We know that we've got this very Earth-like planet from the point of view of the processes that are taking place. We know we have all these diverse materials and environments. You look at this globe on the left and you see all these different colors. Each color represents a different kind of surface composition. We don't know the exact composition of what those elements are, but we do know they're all very different from each other. And some of them are going to have more water ice and some have more organics. But we really want to know what are those compositions and what's taking place on that surface. So the real challenge though is, looking at that, you can't pick one place to go to. The Huygens probe went to its one location, right? But now we know there's so many different places we'd want to go to. And so with Titan, our strategy actually is to fly and really take advantage of the atmosphere. So I'm going to walk through that a little bit more. So again, diversity of surface materials, it's a high priority scientifically to actually go to different places. And if we can sample the surface and measure the environment, the atmosphere in many different places. So we do that already. We do that in planetary exploration. We do it on Mars, and we do it by driving around, right? Roving with one of the Mars rovers. But there's actually, Titan kind of has an advantage over Mars when it comes to moving around on the surface. And I've hinted at these things already. So the thicker atmosphere, the higher pressure, as well as the colder temperature means that Titan's atmosphere is very dense. So it's 4 times denser than Earth's atmosphere at the surface. And what that means is it's just easier. You have more atmosphere to push on if you want to fly somewhere. If I forget the exact dimensions, but assuming you'd be fine with the cold and and not breathing oxygen, if you could have like wings strapped to your arms on Titan, you could basically use your arm strength to fly, maybe wings, I would say like a school bus wide. And so what that means if we want to do that with a motorized craft, right, it doesn't take as much energy. You don't have to generate as much relative lift because you've got this pillowy atmosphere. And when you combine that with its gravity, its lower gravity compared to Earth, again, that overall reduces the amount of power you need to take up off the ground, right, and fly through the atmosphere. So it makes a lot more sense for us to take advantage of that at Titan versus trying to, drive around bit by bit. I always love this cartoon. It makes me laugh. Now, of course, we know now that the helicopter on Mars has been extremely successful, right? The Ingenuity helicopter that went up with the Perseverance rover. But if you look at that craft, it's really, really small, and it doesn't carry a whole lot, and it's got these really big rotors, right? And so what we want to do at Titan is actually take something that really is the size of a Mars rover, meaning it's full of these big scientific instruments, and be able to fly it from place to place. So kind of almost like a merging of the Perseverance and Ingenuity into one thing that we can fly at Titan, right? And so what's so great about being able to do that is we can go really far. We can go a lot farther than you can by driving on the surface. And it also means you don't need to start with super high resolution images of the surface in order to chart your driving path, right? We can actually get up off the ground, look around, and kind of make our own maps as we need to. All right, so just a little bit of info on the Dragonfly rotorcraft that I've been showing images of. Just to give you an idea, again, this is a standalone, this is a single spacecraft that is going to Titan. It is powered, is designed to be powered with an MMRTG. And so this is the, radioisotope source, just like Curiosity and Perseverance. So it looks kind of very similar the way it's coming off the back. And so from that, we get our power to charge batteries, and we can get, we have pretty big batteries, right? Strong enough to allow us to fly, as well as to make all of our scientific measurements. And that also allows us, we're not relying on solar panels or sunlight at the surface. That would not work at Titan, and allows us to have a long-lived mission on the surface with that power source. For the flight, this is a dual quadcopter. So you can see that's 8 rotors in 4 locations. And the image that you see, this is just to give you an idea for scale. This is the mission PI, the lead scientist, Dr. Turtle, holding one of the prototype rotors, just to give you an idea of how big these things are. And then the communication is actually direct to Earth communication. So there's no satellites at Titan, right? We don't have any GPS. We don't have any communication satellites. We're going to use this large antenna that you can see in this image to point back at Earth and communicate directly to Earth. The timeline right now, our launch readiness date is in June of 2027. It's going to come a lot faster than any of us realize, and arrive at Titan by 2034. We do this direct atmospheric entry, takes several hours. And I already mentioned this fun fact, but it's a similar latitude and same time of year as when Huygens was there, which is a great benefit because we have that data from the Huygens descent to have an idea of what to expect in the atmosphere, sort of with the weather, during that time. The landing site that we're going to, I've highlighted here in the box. It's a region we actually are going to land in some of those dunes, the sand dune areas. And you can see the approximate landing ellipse, and then ultimately traverse up to the Selk impact crater. And this allows sort of access to a whole range of materials that we all think are really important to understand. One is those sand dunes, which are just organic sediments that are linked to the atmospheric source, that haze source. Then there's these interdune areas where you can see exposed water ice, the water crust. And then finally, the impact crater is a place where, again, there would have been liquid water in the past. After the impact, you would have had organics and liquid water mixing. And we really want to know what kind of chemistry took place there. What kind of, that was like an experiment that happened on Titan, billions of years ago, millions of years ago. What are the results of those experiments? This image on the left gives you an idea of the scale of the dunes that we expect to find. This is an image coming from the Namib Sand Sea, but they're similarly created and similar sized dunes. And one key thing, I always like the picture on the bottom left, which includes some members of the Dragonfly science team. There's these wide interdune flat areas. And that's why it may sound like, wow, you're going to land on dunes? That's crazy. But no, actually, there's going to be a lot of locations in those dune fields where actually it's quite wide and flat, and there will be safe landing locations there. The exploration strategy, kind of going from left to right in this plot, is going from the dune fields up into the impact crater again to be able to access all of those different types of materials. Some of the numbers on this plot, they're going to go up and down a little bit. We're in the design phase still in terms of capability of the flight, et cetera, as we refine the design, but you get the general idea. We can go, tens of kilometers, maybe 100 kilometers in the prime mission, which is over 3 years. And the idea is we'll be able to explore dozens of sites as we're kind of making our way from the landing area up towards the crater. Like this graphic, just to give you an idea of one of the concepts for how we're going to do this flight. So as I mentioned, we don't already have these high resolution maps of Titan's surface. And so we're going to be using this approach frequently where we call it like a leapfrog. So you take off, you fly over a site you plan to go to, a pre-selected site, and you keep flying, and then you scout a new potential landing site, get some, topography data, get some imaging of that, then come back and land at the site you already decided on. And then while you're sitting at that one location doing science, then you'll also look at all of the imaging and data from the scouted area to pick the next landing site. And another key thing I like to emphasize is that the flight itself, you can see this first bullet, we might fly for something like 20 to 30 minutes. And then we may only do it every 2 to 3 Titan days or TSOLs, which really translates to flying like at most once a month, maybe once every 2 months. So we do spend most of our time on the ground doing our science, but the flight is obviously a key component, and we get really valuable data during flight, and it allows us to really put our landing site into the context of everything around it. We have really multidisciplinary science that we're going after that addresses these 3 main goals that you see on the left, kind of color-coded. So we've got prebiotic chemistry. I emphasize that one a lot because to me, that's the most exciting one. It's up on the top. It's one of the main reasons we're going to Titan, is to look at the chemicals, the composition of those chemicals on the ground, and see, have any of them kind of progressed towards what we would think of as building blocks that are important for life, things like amino acids or nucleobases, things that we know are really important in order for you to then get the larger chemical structures that our biochemistry functions on. We're also really want to understand the environment. Habitability is often described in this very narrow way, but there's a lot of factors that can go into what makes an environment habitable. And we really want to explore that at Titan's surface, especially if you think about methane as being an important component. How does that cycle through the atmosphere? Can you define a habitable environment in terms of the availability of methane or liquid methane? As well as, can we say something about, are we mixing with that interior ocean? Oops, sorry, got ahead of myself. And then finally, the search for biosignatures. This is like chemicals that we think are indicating to us that there actually is some kind of maybe active biochemistry there. And this is really builds off of the other prebiotic chemistry goal, which is, okay, we measure all of the stuff. Now, when we put it in context of the environment and everything we know, what do we think it's telling us? Is something popping out to us as a potential, indicator that there is something really interesting going on there in terms of a biochemical cycle. So we do this with a scientific payload. So again, the goal of the flying on Titan is not just to fly because it's fun, even though it is, but it's to bring these instruments from place to place and make these measurements. So here you can see on the left is our full instrument suite. We have 4 instruments plus a sampling system, which is Draco, the red. And you can see how they're populated throughout the rotorcraft on the right with all the color coding. So this includes the mass spectrometer. So that is the instrument that is going to be doing the chemical composition measurements and molecular composition measurements. And as I mentioned, that's the one that I have been working on. The red is our Draco is our sampling system. So this is a drill that drills the really cold cryogenic surface and delivers a sample to the mass spectrometer to measure it. We have the Dragons instrument, which is a gamma ray neutron spectrometer that looks at the bulk elemental composition around the surface. We have a meteorological and geophysics package called DragMet. And then finally, we have a full camera suite. So I'm going to go through a little bit more info about what these instruments are doing at the surface to kind of help us get at these big science questions. So the cameras are really modeled off of the imaging systems that we have had, for example, on Mars with the Mars rover. So so these images that you're seeing here on the left are all actual images that have come from a somewhat similar, camera imaging suite on the Mars rovers. So these are Mars images. And so the idea is we've got kind of cameras all over that give us, a look at what's around us, what's in front of us, also kind of forward down where we can see, where are we, what does the surface look like in front of us, or where are we aiming at? We have the downward cameras, again, to see what we're sitting on. And then finally, we have these microscopic cameras, which can get at a very high resolution what the ground looks like. And so, for example, if we're in an area with a bunch of dune sand, we can get a really good idea of what do those dunes look like and what are they made of. And then on the right, I want to point out, we have this LED array, which allows us to illuminate the surface in different colors. And then by looking at what comes back at us, we can look for differences in the surface composition. So this picture on the right is from some laboratory demonstrations of this microscopic camera and the laboratory array. And this is organics that mimic Titan materials mixed up with water ice crystals in using that LED and microscopic imaging. And you can see right away by looking at it, right, that you've got orange and yellow colors coming from the organic materials, and then you see the white from the ice. And this is an example of the kind of view we may get when we're on the Titan surface. Another cool thing, the LED array includes a UV wavelength as well, like a black light. And from that, we would expect certain organic molecules actually to really light up. And you would do this imaging at night and see what pops out and get an idea if there are specific areas of the surface that have some molecules that we might be particularly interested in. We've got the meteorological and geophysical monitoring. So, looking at atmospheric conditions, things like methane concentration, look at temperature, pressure, winds, do things change throughout the day? Do they change as we move around? Really getting a feel for the environment, characterizing the environment that we're in. Then we can also have sensors that sense the surface itself, trying to look for things like how porous is it? Can we put some constraints on the material? And then the interior, we're interested in looking at, is it possible for the organics on the surface to ever get down and mix with the ocean? And what can we learn about how far down is it to that ocean? We have a seismic measurement that will help constrain that as well. So if Titan is very geologically active and we can measure any Titan quakes, then from those measurements, we can get ideas to help us constrain how thick that ice crust is and how far it is down to the interior liquid. The instrument Dragons, which is the gamma ray neutron spectrometer, I mentioned it's going to measure the elemental composition around the lander. So it's sort of this integrated instrument of you can see the cartoon, right? It's shooting out neutrons and it's getting back neutrons and gamma rays and trying to get an idea of what materials are there on the surface. So the idea is we can classify things going from site to site, and we can understand, is this a big chunk of water ice, or am I sitting on, as in this cartoon, a layer of organic material, maybe on top of water ice? Is this area different than the place I just landed? And is it worth us, digging into the surface and expending some more energy to really, get an idea of the composition? Or do we just kind of fly, a little bit and land someplace just like where we just were, so we don't need to take a measurement again? That's the kind of science that we can get out of the Dragons instrument. And then finally, the final thing we do at any landing site location, if we make the decision that we want to take a surface sample, and then we would do that, we would drill into the surface with our sampling system called Draco. And then this is actually a pneumatic sampling system, so like a vacuum cleaner. And again, here we're taking advantage of the fact that Titan has this thick, dense atmosphere. We don't have to scoop and try to dump materials. We can actually just suck it up, again, like you would with a vacuum cleaner. So we drill into the surface, you can see in the cartoons, create a powdered samples from whether it's water ice or if it's organic material. And then you suck it up like a vacuum cleaner. We have all this pneumatic tubing. We've seen the bottom left cartoon where it says collect. Then we have these cups that are in the stream if we decide to collect that sample, and some of it goes into the cups. The rest just gets dumped outside. of the lander. And then once there's a sample in the cup, it can be moved over to the instrument to look at the composition. The images on the right just give you an example of some of the simulants that we've used to test the system. We want to test it and make sure that the plumbing doesn't get totally clogged up when we're running it. We're doing a lot of tests at the right temperatures and pressures, make sure it will work very well on the surface of Titan, as well as be robust to a whole bunch of different surface compositions and, surface environments. So then finally, once we take that sample, it gets measured by the mass spectrometer. So the mass spectrometer is an instrument that is able to look at the different types of molecules that you have in a sample. And it does this by first converting the solid materials into ions. So molecules with a charge on it, and then sorting out those ions basically on their molecular weight, how much they weigh, separating them out. And so when we do that, we can look at the different compositions on the surface and get an idea of what's there. And we get information not just from the masses of the molecules that we see, but also from the way in which we ionize them. So this plot on the right, it's a little complicated, but you're mostly supposed to get the idea. There's a whole big range of molecules and molecular sizes and shapes that we can measure with this instrument. We have a nice wide mass range, which is great to look at, pretty large molecules. And we use these different techniques to make the ions. One is a mode that we call laser desorption mass spectrometry mode. I'll talk a little bit more about that. Another one is GCMS. And this plot just shows, if you look at the color bars on the left, just those different approaches help us span a wide range of molecules, some that are super refractory and they don't want to get into the gas phase at all. They're larger molecules, they're not very volatile. And then we can also access some that are more volatile. So just to talk a little bit more about that, on the left, we use the LDMS mode to do what we call sort of a broader survey of the sample. We'll get the sample delivered, we shoot a laser at it. Even large molecules that are in that surface can turn into ions, go into the instrument, and we can measure them. And that graph you see there with the red lines, that's what the mass spectrum, will look like. You've got sort of molecular mass on the bottom, and then you get these peaks where you've got a lot of something showing up. And we also have techniques that we can use if we see a big ion to fragment that and look at the pieces to tell us information about what is that molecule. Now going over to our gas chromatography mode or GCMS mode, that's a little bit more of, I think it was a selective and sensitive technique. And in that case, we have a sample that we're heating up in an oven to get off anything that will volatilize at high temperatures. And we also have some chemical reagents in the cups that go into the ovens that allow us to take molecules, for example, an amino acid that isn't necessarily going to be volatile enough, and we transform it chemically so that it is volatile, and then we can send it through the instrument. And then we can see these molecules, and the GC just adds a second element of separation. So it's these really long, thin columns. They're like the width of a human hair and 30 meters long, and they're just coiled up. And you send a mix of molecules in, and as they flow through the column, they separate out based on things like size and the type of chemical that they are. And I always think about it like, it's like if all of us went out to the racetrack and we'd all start at the same time, running in laps, but eventually everyone's going to spread out and they're not going to finish at the same time. And like I'll be in the back. And that's, sort of how the GC works. And then they all go into the mass spectrometer at these different times. And that's another way to separate out what might be very complex mixtures. With the GC mode, we're also getting at some of what we think of as important chemical biosignatures, which is this concept of chirality or handedness. So you see that hand cartoon with the amino acids at the top. Molecules like amino acids have a handedness, which means that they look the same and they're connected. All the components are connected in the same way, just like your hands, right? So your thumb is next to your four fingers, next to your middle finger on both your hands, but your hands are not superimposable, right? They're mirror images of each other. And so you have these molecules where you get that too. They're mirror images. But what happens in your body is that the chemistry going on in your body really only uses one of those, not the other one. If you go out in the universe and you find amino acids made abiotically, you'll get a pretty even mixture of both of the hands, so to speak, both of the enantiomers, we call it. But in your body, we use exclusively left-handed amino acids, for example. And so finding amino acids where you have a big difference between one versus the other hand is considered a potential biosignature. And that's something that we can measure with this instrument. All right, so I think I'm summing up a lot of the details, but just to kind of bring it home, the Dragonfly mission, you know, it's really kind of a revolutionary exploration where we are going to what's classified as an ocean world, right? Because it's definitely got liquid water in different places. And we're trying to go to these different surface environments to understand, you know, how far does chemistry take you? When you have this much chemistry going on, how far can that take you towards what we know is important for providing the ingredients for life? And what can we learn about those processes that we can apply to understanding our own planet, as well as, you know, when we look out in the universe and we see all these other amazing, you know, exoplanets, you know, what can we learn about the processes that could lead to life? I have a video here. We'll see. Yeah, it does work, of some test flights that we took with one of the test zones out in California, and it has captions, so I won't talk. So one thing, I don't know if I explicitly said this, but Titan is far enough away that this rotorcraft has to operate autonomously when it is in flight, right? So there's no one who's going to be at a joystick flying it around and navigating it on surface. It has to be able to, once it has its commands to fly to a specific location, it has to be able to navigate itself. And so that's the kind of software that test was looking at, is how to do that autonomous navigation. All right, so finally, this is my final slide, at which point I'm really happy to take lots more questions if you have them. But I'll point you to our project website. If you can't remember this URL on the bottom, that's fine. You can just Google, you know, Dragonfly mission APL, and it'll come up. And you can get a lot of these videos and movies that we have. We have also a really great movie that shows how the whole sampling chain works, that was made at Goddard, to understand that better as well. And so with that, I will thank you all for your attention. Thanks so much for having me, and I can take some questions.
That was amazing. Thank you so much. I know I have questions, but anybody else want to go?
Yes, to start with, did you say that the temperature in the atmosphere was minus 290 F?
I did.
How's metal in that in your helicopter going to your drone going to behave in that kind of weather, in that kind of temperature?
So that's a great question. I'm putting up this picture of the drone just to help us talk to it. Well, so obviously we have to make sure that any of the metals that are the structure that are exposed have to be compatible with that temperature environment, right? We can't pick anything that's, you know, going to drastically change its mechanical properties when it gets exposed to those temperatures. So we're really cognizant of that in putting together the structure of the drone, especially the parts that are exposed. So for example, you know, the skids, right? The legs and the skids that are out there, these, you know, some of you see the rotors, the camera windows. The drone itself, you know, we need to keep everything inside warm. The instruments we build can't survive at that temperature. You know, they would much rather be more like minus 20 to 0. And so the lander itself is going to be covered in insulating foam. And then there'll be like you know, an encasement around that foam to protect it from the environment. But this area where it kind of looks like shiny and pretty, this is resembling that encased foam. And so the
Would that
majority
be
of the interior will be at a warmer temperature.
Would that be titanium or a titanium alloy or?
Yes, lots of titanium. I can't speak to every single component, the metal, but I know for example, for like our instruments, you know, it's a lot of titanium.
And cameras fogging up in the cold.
Yeah, so that's a great question. That's one that has definitely, it comes up a lot, you know, when we're working through the design. The thing about the Titan environment is that once we're there, we will be the warmest surface. So there's not going to be anything in the atmosphere where we are that's going to want to condense on us, right? If it's a vapor in the atmosphere, we don't have a cold surface to condense against. We have there's some papers out actually where one of the team members looked at, well, what about when we go up? Is the methane vapor, could the humidity be such that it could condense out? And we're able to show that even at the highest humidity conditions, we don't experience enough of like a transition and a cooling to lead to the condensation on the camera. So our biggest thing is to make sure we don't bring like water vapor with us. that could cause that problem, that we, you know, we keep those camera lenses nice and dry. And then once we're at Titan, you're not going to have water vapor at those temperatures.
Okay, fantastically complex mission. Best of luck.
Thank you.
Arjun, go ahead.
Thank you. So, question, how long would the delay of the radio signal from Titan to Earth be?
That's a great question. So it's about, you know, it's going to vary a little bit, but let's say on the order of like 80 minutes. 80 minutes, and that is the time, that's the transit time for like a photon, you know, one signal to come back. And then, so part of the trick isn't just how long that takes, but when you're sending back a bunch of data, we don't have this like big high data stream, right? Because we're aiming that antenna at a telescope all the way on Earth. And so our data rate is also kind of low. So when we're talking about a picture we take on the surface, when we go to downlink it, it'll actually take a very long time to get to the surface as we send it bit by bit.
Okay. A few more questions. So the like the drone which you showed in the video, was that like the actual drone, or was it just like a model done for just for simulation purposes?
Yeah, the drone we showed in the video is just it's a test drone to test out the software and how the software does the navigation. So it wasn't in any way made to look like this Dragonfly drone that you're seeing on the screen now. What it's meant to do, though, is to carry some of the instrumentation that will have that help with the autonomous navigation. And that way they can test, okay, does that actually work? Is it getting the info it needs? Is it processing it fast enough? Is it making the decisions? Is it keeping itself stable? Is it figuring out where it's going? Those are the kind of tests that you know, that was representing that we need to do to prove that we can have something that can navigate itself without us telling it what to do every second.
Okay, one last question. So how do you know that if it flies on Earth, it's going to go and fly on Titan? Because of the cold temperatures, maybe like the gases might be a bit more dense. And that's one factor which I can think of. So it'd be like harder for it to push down.
Yeah, no, these are really great questions. These are the kind of questions that we have to ask ourselves constantly when we think about how are we testing this and how are we proving that this will work. It is impossible to perfectly mimic the planetary environment in a test on Earth. Even if we got the temperature and the pressure just right in like a giant chamber, we can't mimic the gravity, right? We can't mimic the change in that. So what we have to do is we have to think about, well, what is the most important factor of that? Maybe I don't have to have the temperature and the pressures and the winds exactly as they would be on Titan, but I have to understand the physical processes that are taking place, like, and the physics of how it's flying, and make sure I'm mimicking the ratios of these different things. So you have to kind of think it through. You have to do a lot of analysis first to design your test. And then you do a test where you say, okay, well, this test that I'm doing at these conditions is the equivalent of exactly what would happen in this other place at these slightly different conditions. And that's what we have to do for a lot of the stuff that we do at NASA, right? Because it is, we call that test as you fly, and it's hard to ever perfectly do test as you fly.
So it's like a lot of math, right?
Oh, there's so much math, yeah.
Okay.
Lots of
Thank you.
models, lots of computer models, lots of math, but it all comes back to fundamental principles too, which is always fun when you come back to those.
Okay, thank you.
Yes, great questions. Thank you.
How about Gary? You want to go next?
Yeah, thanks. Two very related questions. So one, how are you powering this? And a corollary to that, how long do you expect that power to last? And I'm sorry, I'm going to tack on a third one. If it's like nuclear thermal, are you worried about, I mean, if there is something alive there, are you worried about contamination?
Yes, that's a great question. So great, 3 questions. So one, so we are using the nuclear, right? The MMRTG radioisotope source to charge the battery. Right now, the predictions and the length of our cruise and the lifetime of the MMRTG are such that it should last beyond our prime mission. So I said we've got about a 7-year cruise, and then we've got a 3+ year prime mission on the surface, and that power source should last and should continue charging our batteries through that into, we hope, an extended mission. And then eventually it will start to take longer and longer to charge the battery. But we have plenty of power to get through, what I have shown you as, our goal of getting to that impact melt structure. The third part of your question, we actually have to go through a rigorous process with NASA and the Planetary Protection Office, which classifies that kind of risk, for example, right? What is the odds that you could actually do something or hurt something when you're on the surface? And with Titan, even though we're really interested in exploring these places on the surface where there was liquid water, right? There isn't, where we're going, there's not going to be any currently. And the crust is thick enough and the distance to the interior ocean is far enough that it's all a probability game. The probability that there could ever be an impact of something we brought with us chemically, or, something that we could do with the nuclear power source is going to impact, any place that would actually be an environment that could support life as we know it. And so that's partly how we address that. And so that office at NASA kind of, approves and classifies the planet and approves it. And then we can get that go ahead to go to that location.
That's right out of science fiction. It's almost like the prime directive on Star Trek.
It's our version of, yes, it's our version of that. That's right.
Daniel, you want to ask your question?
Now, here's the question. How come the Dragonfly mission is called so?
That's a good question. So we named it, it's been quite a long time now. I want to say almost seven years since we were first conceiving this mission. And, we were certainly inspired by the flight to name it after, something that flies. And there's a lot of reasons that the Dragonfly name suits really well. We've got those like the double rotors, is like the double wings of Dragonfly. Another thing I'll point to, I don't think it's quite on my background, but the one logo for Dragonfly, you can see it's like, it kind of looks like a dragonfly, and it's got this double helix and hexagons, the way it was drawn. Also, when we came up with that logo to go with the name, it was also super evocative of the types of chemical structures we're looking at, whether it's that helix of DNA makes you think about biochemistry, but also even just aromatic molecules make those like hexagons. And that's another thing we intend to find. And so there's just a lot kind of in thinking about flying around. You've got all these, eyes looking at everything, that made us think of what this mission was all about. We also thought about Firefly because of the nuclear rear.
Sorry, was that again?
We thought about Firefly too, because it has like the nuclear rear end kind of glowing. But I think there's already a TV show and a couple of other things named Firefly that we didn't want to mess with.
But it also got multiple cameras that are multiple eyes. That's also why it's called the Dragonfly.
Yeah, that's part of it too. Yeah, you can kind of see them in this. I love this. This is a relatively new rendering of what the rotorcraft will look like, update it to our latest design and you can see all of the cameras.
Is that a smiley face?
Doesn't it look like a smiley face? It does. I think that was a maybe by accident. I mean, the camera eyes are kind of where you would want to put eyes, right? And then the little thing that looks like a nose sticking out is a sensor, and then it has the shadow that kind of makes it look like a smiley. Yes, that's another reason I love this picture.
And it's got little antennas too.
Oh yeah, it's got lots of stuff sticking out all over.
Ken, go ahead.
Yes, you made a really great case about why why Titan is, unique in our solar system. But in terms of the atmosphere, and I'm not sure if you already covered this, but I think you said it was like about 10 times thicker than Earth's atmosphere. And did you cover why they think that atmosphere, I mean, I think that's the only moon with an atmosphere, right?
Yeah, no, that's right.
So why?
So what I said is it's not that it's thicker 10 times, it's 10 times more extended compared to Earth. Like the
Right.
atmosphere goes really high, and that
Yes.
relates probably to its lower gravity, right? It can't hold the atmosphere as closely to its surface, so it goes up a lot higher. Why? That's a great question. Why is Titan the only moon with an atmosphere? I mean, that's something we'd love to know. We know how the atmosphere happened, or we think we understand, where the atmosphere came from, but we don't really have all the details. And why is Titan so unique in that even if other moons had been able to outgas some level of atmosphere, they clearly all lost it. And why is it that Titan has been able to hold it? Is there constant replenishment of it coming from the interior materials? That's one open question. Or did it all come out from the interior at one time? We have a lot of questions about the history of Titan's atmosphere that are not yet answered. And some of the data that we'll be able to get with Dragonfly on the surface will help provide more information to help us understand that.
Thank you. It's great talk.
Mario, go ahead.
Dr. Trainer, thank you for that great presentation. My question is around the molecules that you will be able to detect when you get to Titan. It has been hypothesized that some of the primordial molecules that led to life on Earth, even before bacteria, before amino acids, were self-replicating RNA molecules. Will you be able to detect those types of molecules with the instruments that you have on the lander?
Yeah, that's a great question. So the kinds of molecules we would be able to detect are like the building blocks of those types of molecules, right? So I talked about things like amino acids or nucleobases. So the unit components, or maybe some like oligomers where you can get a couple of those strung together. So that buildup of do you see those types of molecules, and do you see them starting to maybe form some chains? That's the extent of what we would be able to see. We don't have a payload element that could look for like big RNA and confirm that it's active, right? Confirm that it's it's doing any of the replication. That would be a fascinating next mission, something that is a little bit more like we're not really a life detection mission, right? We're a chemistry mission. And so that would be the next step, is to send something that could actually really pin down whether you've got some kind of activity that we could point to life.
Okay.
Thank you.
There's a couple more questions, and there's one in the chat from Peter Chen saying, asking, is there any evidence of lightning activity on Titan?
Yeah, I think this one gets very debated. We don't know for sure. Yeah.
And he says he's thinking that, perhaps that would help with the formation of complex organic molecules.
Yeah, I mean, that's something that's definitely been hypothesized as an energy source on the early Earth for doing that, right? There's definitely models that look at what kind of synthesis can you get with lightning strikes in a certain atmosphere. I think here on Titan, we make so many organics the other way. It's not required to have lightning, but obviously, if we were able to observe or detect lightning in any way, that'd be fascinating.
Go ahead, Dwayne. You're muted.
Yep, it warned me. great presentation. This is so exciting. I just got done watching Ingenuity do another flight today, and like this is the fact that this thing is the size of a tank almost, I don't know, or a car. It blows my mind. You're really taking advantage of the atmosphere. I love it. I had like 3 questions tonight. I love this format. You answered 2 of them, but so my last question, you talked about the cameras being like curiosity. I'm dying to see Saturn from Titan or Earth in the night sky from Titan. I'm sorry, we're all telescope geeks and the transparency is probably horrible, but the seeing is perfect. You know, I don't know how it works, but are there any cameras that can look up?
So the thing about Saturn is that we're actually on the opposite side of Titan from Saturn. So we couldn't see it anyway. And that is, you know, by design so that we can communicate with her. And also, yes, we would not be able to see Earth through the atmosphere with any of the types of imaging systems that we're carrying. So
It's a shame.
it is. I know it would be really, really cool, but we would want like an orbiter of Titan for all those things.
Okay, Alice, you want to go ahead? And then I
Yeah.
think we should wrap it up because we have other stuff to talk about. Or maybe one more.
Yeah, can you hear me okay?
Yes.
Yeah, I've been having trouble with microphone. I have a comment and a question. Just a comment about a few questions ago when you were talking about life on Titan, and there probably wouldn't be any. I'm always joking with I have some relatives who are contractors at Goddard, and they work on Europa Clipper in a tangential way, and I'm always whining at them, don't touch Europa, you know, leave Europa alone, you know, but I'm only half joking, by the way. I mean, does NASA have some, maybe not for Titan, but does NASA have some guidance on, like, what do you do if you find evidence of life? I mean, how do you?
Yeah, that's a good question.
Since they're looking for it, they must have thought about it. And what happened? What do they tell the public? What happens after that?
There are some discussions, you know, that happen in the community. I can't speak to closed door discussions that might happen and in NASA headquarters. But there's a lot of discussion in the community about, you know, really will we know it if we find it? That's a big area of discussion. How will we even know it? Will we recognize it? What will, you know, short of like, landing on Europa and having a big tentacle come up and grab you. You know, we joke about that too with Dragonfly. We figure if we see any life moving around, like even if it eats us, it's okay as long as we get the picture back. Then we win. So, you know, discussions about like how would we communicate it to society? I think that's a really important thing to think about, that I don't know if I'm hearing those detailed discussions yet. It's more about like how would we even do it if we find it?
Yeah, because you had that whole thing in 2001 where everybody was scared about the massive societal impact of this thing being found on the moon.
Yeah.
And so, I mean, I'm not sure that anybody would really freak out like that. I mean, they just kind of go, okay, well, and a lot of people wouldn't even believe it.
It would be a big
that's the
big
thing
endeavor.
about half the people in the United States would say this was done in Hollywood, so it's okay.
Thank you.
May I do mine real quick one?
Sure. And then Arjun, and then we'll wrap up the questions.
Okay. Carolyn Porco must be absolutely fascinated by this. Is she involved in any way?
She is not directly involved, but I will say that a lot of the people on our science team, including the mission PI, Dr. Turtle, were members of the Cassini science team and working with Carolyn for a really long time, years and years, and working on, you know, the images of Titan and processing the images of Titan. And so I know that, you know, that community all talks a lot, right?
Yeah, she must be over the moon, no pun intended, over this mission. Thank you. Thank you for a wonderful presentation.
Yeah, thank you.
Go ahead, Arjun.
Okay, so my last question was, is there a limit to the complexity of the chemicals which the sensors can detect?
So there is a mass limit, though there's a limit to the size. And then if you know, it's not that complexity necessarily scales with size by any means, but that is a limitation. So the instrument has a mass range of something like between 1,000 and 2,000 mass units. So, you know, that's pretty big molecules, but not something as big as like, you know, a whole, you know, big DNA or something, right? So.
Okay, thank you.
Okay, then I'll ask my question is, are you worried about, like, so this thing, the atmosphere is so thick, it's kind of like, almost like swimming and somewhere between swimming and flying. Are you worried about any big storms and, you know, hurricanes or any?
Oh yeah, that's a good
things?
question. So one thing I mentioned is that the seasons are similar, but they're really slow. So the Titan rotation is slow. The change in solar insolation is very slow compared to what we're used to on Earth. And in fact, you know, when I cite a surface temperature, I'm not giving you a surface temperature that's like an average. I'm talking about like, that is the temperature, like all the time. Like maybe it only varies a degree or two, right? So it's not as dynamic as the environment that we have. Now I did tell you that there were clouds and I told you there were rainstorms. So it's not that there's no storms, but first of all, the time in which we're landing and we'll be operating the prime mission is not what has been observed to be the rainy season, so to speak. So it's actually after our prime mission that you would even have a chance of, in the location that we're at, seeing any kind of rainstorms. And then even if we do, you know, the level of winds that you get and the level of like energy in the atmosphere is just a lot lower than what we think of as like big storms. So it's not going to be as dramatic.
Cool, thank you so much. And
Sure, thank you,
I'm
everybody.
an antenna engineer by trade, so I have antenna questions, but that's for.
Oh,
that's
don't
not-
ask me those.
That's for the other team members, yeah.
Yeah, that's gonna
Okay.
get out of my technical realm.
Well,
for
again,
sure.
thank you so much. That was terrific.
Thank you all so much for having me.
Okay, so let's see if I can share my screen once again. Are you guys seeing a PowerPoint slide? Okay,
Yep,
thank you,
yep.
thank you. So we have a couple of announcements and then some Astro images to share. So one is we have our first of the year star party coming up in just a couple of days. The forecast was looking really good. It's not so good, but you know, these things change. So let's keep a hopeful eye out. So this Saturday is our first members, and then next week, Saturday, the 25th, is our first public star party. So I'm hoping that we'll get good weather and that some of you folks with your telescopes can come out and share views. Also, it may be worth, I don't know if anybody's nutty enough to do it, but the possibility of seeing all Messier objects in a single night is that time of the year when you can do a Messier marathon, and it corresponds to the 18th. I wasn't planning on staying up all night and staying there, but maybe a key holder will if we get good weather and somebody wants to do that. So anyways, the rest of the star party schedules are here as well. But really I'm looking forward to this this Saturday. I'll be there in the observatory. There's an Astro School thing I want to mention, but before I do, Michelle, do you want to make a quick announcement you had?
Sure. Sure. My name is Michelle Heimowitz, and I'm kind of an active member. I come and bring my telescope to the public star parties with my husband. And I'm a teacher at North County High School in Glen Burnie, Maryland. I have a pretty active astronomy club, and we're a STEM school. One of our pathways is Earth and Space Systems. And I have been holding a stargazing party every month. And it's been somewhat successful. But coming up in April, I want to have having an Earth Day. My associate who's teaches green tech, he's going to be showing what he's growing in his garden, and he's actually picking up chickens today. He's going to start raising chickens organically in the classroom. And I want to show students what the sun looks like through sun-safe telescopes. We have a whole lot of telescopes that have been donated to our school. Thank you for those of you in the club who have done so. I don't think all of them, I know all of them don't have sun filters. So I'm curious or interested in having someone from the club maybe come out to talk to us about how to make those, but also to show students what the sun looks like and to talk about the sun. The Earth Day event is on April 19th. It's a Wednesday during the day, of course, to see the sun from noon to 3:30. I sent an email through the HAL group yesterday because Victor said it was okay to do that. Maybe it was this morning. And I am hoping to get some volunteers. My husband has his own personal hydrogen alpha telescope to look at the sun, but I'm absolutely interested in welcoming any other volunteers that would be willing to come out and, you know, bring their hydrogen alpha telescopes or sun safe telescopes to look at the sun and talk about the features and teach students about what they're seeing.
Hey, Michelle, it's Phil. I'll let you know, I've done this with you before, and it was great. Even the police came out to look, and I'm going to put it on my calendar, so I'll be there with my lunch. And if I could manage to handle and watch a white light scope at the same time as the HL, I'll bring both. So we'll follow up more offline so we can keep the meeting going.
Terrific.
Okay.
Thanks, Phil. And yeah, there's a message posted to the Google groups. If anybody sees that, please, you can respond to Michelle directly and coordinate. So that's terrific.
Thank you.
Okay, Phil, so you're next too.
Hey, Bob Savoy, are you out there? Bob was going to join us.
Yes, I am.
Oh, great. So Bob and I are co-hosting Astro Schools, and we are planning on holding an Astro School on April 13th, which is the second Thursday of the month. This is the third Thursday of the month. We're going to do this on the second Thursday of the month live at Robinson Nature Center. And right now, we will not be doing a Zoom along with the other one. We just need to focus on the school and not on all the technology. So we'll figure where that's going to go. So we're finalizing what the topic's going to be, and I'm going to turn it over to Bob for his comments.
Just a very short comment. We're really excited about Astro School, and the first one is going to be on the second Thursday, the April 13th. And we're not sure exactly what we're going to be doing, but it will be a lot of fun.
So more to come. So watch your emails. And like I said, this one's going to be at Robinson Nature Center. And when the weather's nicer and it makes sense, we will probably do some also at HALO at our observatory. So that's it.
What time, Phil?
Okay, so good question. It's going to be 6:30 to 8:30 p.m. on that second Thursday.
Thank you.
Yep.
Phil, is there going to be anything like a sign-up sheet or a reply to email chain?
No, it's going to be announced. The biggest problem we should ever have is that we overflow the room. That would be a great problem to have. But no,
Okay.
So it's just going to be very much like this meeting. It'll be advertised, and come if you can. We'd be thrilled to have you.
But all of the HAL members, including kids, are invited.
Right. By the way, this is a members only event. So this is a benefit of being a member. So this being focused on our members and you know, we do other things throughout the year for our guests.
Daniel, I see your hands up. Did you have something?
You're on mute, Daniel. You're on mute. We can't hear you.
Last night, I took a video of the International Space Station. I put it on the HAL Facebook page. Did you all see my video?
Not yet, but I do appreciate you bringing that to our attention. That's gonna be great. So we'll take a look.
And no, did anybody of you see my video on the Facebook page of the ISS? Anybody?
No, I'm sorry, I didn't. I hardly ever go to Facebook these days.
But I took a video of it, and if I wanted to have a picture so I can present it to the public on a Thursday night, who do I email it to?
Cool. Well, yeah. So, you know, if you put something up on Facebook and you want to call our attention to it, just send an email to the group, you know, like we always do. You've done that before. Just send an email saying, hey, it's on Facebook, and then we'll all go take a look.
And actually, you have just done so, because I'm going to go now and log into Facebook and have a look.
And then what's the email address I send the message?
I'll send you a note, Daniel. It's Howard Astro.
Howard Astro at googlegroups.com. But yeah, we'll send you a note offline.
We'll send you a note offline.
Thanks.
Okay.
All right. Thanks.
Thanks, Daniel.
So let's move on. Were you guys done, Phil? And
I think so. Bob, are we done?
Bob?
Yes, we are done.
Okay, terrific.
We're done.
So next we'll go through some images. And Steve Gauss, are you here? It looks like this is a picture of Venus.
Wow.
Oh, there you are. Would you like to say
No.
something about this? You're muted.
It's beautiful. Whatever that's.
Okay, yeah, here I am. Yeah, the Venus is getting pretty low, but it's pretty bright now. And this, I think I took this the same night of the conjunction of Jupiter and Venus. So I had a wide field image of the two. This was the close-up of Venus on that night.
Cool. I guess you can see the phase there.
Oh, yeah. Yeah.
What telescope did you use?
This was the C14 with the Zero 2600 MC. That's my primary telescope.
Wow.
Nice. But let's see, this would have been with the Hyperstar. So this was just, I think this was after I removed the Hyperstar and I took this image of Venus.
It is very, very pretty. You hardly ever see that.
Yeah, the atmospheric dispersion is really greatly captured.
This was pretty low in the sky.
Yeah, I guess if you had one of those dispersion correctors, then it would look mostly just uniform color, right?
Right. Oh, yeah. Yeah. You can do it. You can get it during the daytime when it's higher, but then the sky is usually pretty ripply from the heat of the sun, and it's hard to get a good image.
Oh, cool. Well, you hardly ever see anybody do Venus, so that's really cool. Thank you.
Yep.
Jim?
Yeah, just a picture on February the 28th. I thought it was going to be cloudy the next night, so I went out and got a shot over Towson University's clock tower there of Jupiter and Venus.
Cool. That's very scenic.
A little trick that Herman Hein taught me years ago is, get something in the background if you're doing a conjunction.
Nice. I guess foreground too.
Was that a regular camera or just that wasn't a telescope?
Yeah, no, that's just
like an
a regular,
iPhone or something.
It's just a regular Canon EOS Rebel. I think it was it was with a standard kit telephoto lens. I forget exactly, it was probably like 75, 80 millimeters.
Nice. James Willingham, I don't, is James on? He doesn't usually attend. These are a couple of pretty cool images, a conjunction and a commentary picture with a background galaxy there.
Yeah, and Victor, if I could add for that one.
Yeah, please do. I don't know what to say.
Picture on the left with the comet. I forget the name of this comet, but James took this with a remote telescope in Chile that he rented some time on. And so that's how he was able to grab this image.
Yeah, pretty cool. Okay. Arjun.
So this was an observation of the green comet using a remote telescope. This was the Mars Desert Remote Observatory, and I think it is a 14-inch telescope. So on this one, I had to use like a composite image because I wasn't able to stack the third filter. So I had to mimic it using other filters. And I think I got a good shot. I could barely see the tail. I wanted the tail a bit more, but I think that because of the really small field of view, most of the tail was blocked out. But this was not the data which I took. This was like archive data which was found. You can I gave credits to the person at the bottom.
I see. Okay, cool. Yeah, I can kind of see the ion tail right here a little bit. You can see the pointer.
Yeah, that's what I think I'm seeing.
Yeah. Well, cool. So you were able to get his data.
Yeah, I was just able to access it.
Neat. And did you remove the stars?
Yeah, I removed the stars.
I see. Cool. Very cool.
Thank you.
Greg? Is Greg on?
Yeah. The picture on the left is just a picture of the sun I took through my solar filter on my Red Cat 71. And then obviously the picture on the on my right there is just the mineral moon process picture I took on the March 9th.
Awesome. It's gorgeous. I tried to scale them to be the right size so that, we could, like, I should animate the one in Eclipse with the other one with it or something. But no, very nice. Very nice. Mike Connolly.
Hi, everybody. So this was a shot I got on my 6-inch scope of Orion and the nebula M42, a little over an hour of processing time. I had to throw out a couple hours of other data, but these are with 2-minute subs. And I got a new system and reprocessed it through Deep Sky Stacker. And for some reason, making the adjustments in the histogram and DSS really came out really well versus if I didn't make the adjustments and only did it in GIMP. So this is probably one of my better shots, I think.
I think your learning has, as we all have, it's very nice, and you're learning, like, there's so much to learn and you never stop learning as in this hobby. That's very nice.
Yeah, and it's not clear to me, like, well, why does it work sometimes that way with DSS, but not other images, right? I just haven't figured that out, and that's a little frustrating.
Done colorful. I like the color combination of it, blue and purple and pink.
Yeah, indeed. Now here is one from Jim.
This is Omega Centauri. It's the Milky Way galaxy's largest globular cluster. It's 16,000 light years away. It's 150 light years in diameter, and as seen from Earth, it's as large as the full moon. When I first saw it, it was low on the horizon. Oh, and by the way, this was at the Winter Star Party down in Scout Key about 3 weeks ago. When I first saw it, it was very low on the horizon. It was very bright, and in the binoculars, it was so large and bright and low, and I could see the horizon at the same time. It was kind of scary, like something was coming right at me. The capture on this was 20-second subs, did 30 seconds each in red, green, and blue, and I did 90 subs of 20 seconds each in luminance for an hour of total integration time. And what the 20 seconds got me was kept me from blowing out the center of the cluster and from blowing out this, the centers of the stars. I see I got nice blue stars and red stars color all the way through to the center.
It's gorgeous.
Absolutely
We
incredible.
could do this for Astro School as a picture to explain what's actually happening inside globular clusters, which hold the oldest stars in the universe.
Look at the beautiful blue and red distinction in the stars. And
Thank
the
you.
detail all the way down. It's unbelievable.
And this was just 15 degrees off the horizon when I took this image.
So what I guess the seeing was really calm. The air over the water.
That's one of the attractions of Winter Star Party and down in the Keys is the airflow is laminar, and even if the wind is blowing, the seeing is good.
It's terrific. It's gorgeous.
I have a
Yeah,
picture.
I'm seeing a
I
galaxy
have a
off to the
picture of
side.
Omega. I have a
Is there a
picture
little
of Omega
galaxy?
Centauri that I should send you next time. It's a terrible picture. It doesn't look anything like that. It was taken from Mount Airy at
Okay.
2.5 degrees above the horizon.
All right.
You can
Send it
actually
along.
get it from here.
Send it along. I'll bring this one back
Yeah.
up. We can compare them side by
Right,
side.
right. It's big. It's huge.
Is Brad on?
Jim, was there a little galaxy on that right side there that you just had?
Yeah, I think that's what that was.
That's amazing.
Are you guys still seeing my screen?
Yes.
Sorry, there was some
Yes.
squiggle of line on there I wanted to get rid of.
No, but there was a galaxy he was pointing out.
Oh, I'm so sorry.
I was trying to highlight.
I'm terribly sorry. Go back. Yeah, this little galaxy.
here.
over
Look
there.
at that.
I was like, wow, I mean, you can see this little tiny faint guy, and I was just wondering what it's got to be a galaxy. Like, what is that? Because it's so tiny, so faint, right?
All right, Jim, that's your homework assignment. At next month's meeting, you can bring that back and talk about it.
Great
Maybe
capture.
maybe he discovered something.
My guess is that galaxy isn't all that faint for galaxies. It's just Omega Centauri is just extremely bright.
You
Yeah.
could have
Yeah, I
bright
would be
plates all
surprised
around.
if it's a galaxy, actually. I agree with Wayne.
Oh, I think it's a galaxy.
Oh, you do?
I mean, it looks like it on my screen. I mean, you have the bigger version of it. You can tell better.
Yeah. So the when I took this image, the histogram, the sky fog peak was just barely off the left side of the histogram, and I don't know how far across the data actually went, but apparently I didn't clip anything. But I'd be surprised.
You know, when I zoom in on this, it's just amazing the clarity of what you got.
Wow.
Isn't
It
that?
just gets better.
It just gets better. That's definitely a galaxy. That's an edge-on spiral. I can't zoom anymore.
I'll look into that. I'll ask Fix Insight to annotate the image and see what's in there.
I'm
Yeah.
willing to bet there's more than one galaxy in that photo.
Yeah.
Oh,
If you
yes.
took a
Yeah,
deep
there's-
dive.
I think there's if you go down on the image, I think there's one on the lower left.
Could spend a month just
Yeah, there.
studying this photograph. It's amazing.
It sure is. Yeah, it's when you zoom in, it gets better. That's true. Okay.
Incredible photo.
Thanks, Jim.
Is Brad on the call? Brad Martin? Well, this is a pretty amazing cone nebula shot. And I would like Brad to speak to it, but it's done in SHO narrowband, and it's just a beautiful shot. I think he took it from his deck in near Frederick.
Are we sure that's not a Hubble shot?
It's not. I know that's his shot.
Do you know how long the exposure was?
I want to say he might have said it on the Discord. Does anybody remember? Did he put it on the Discord? I don't recall. He posted this to Discord. I also took a picture of this cone nebula, but I didn't want to I didn't want to have like a competing head-to-head thing, so I didn't put mine in the thing. Maybe I'll send it up for next month, but mine was like 25 hours to get something like this. Okay,
This is sick.
5-minute subs, Victor.
mine, I had 5-minute subs for H alpha and oxygen, and then I did 10-minute subs for the S2. But I'm thinking I should have probably done 20-minute subs. But let's see who's Chuck. Yeah, Chuck's here.
Victor, let me jump in. Somebody just asked a question about, was surprised that there's a Discord group, but you could get to it through the HAL website as a member. You could see the Discord group and join in.
I missed that. Who was that? A question in the chat?
The chat.
Yeah, that's my student,
Yeah,
but he's
yeah.
not a member yet.
Well, you have to be a HAL member to join the Discord group, but yeah, there's a Discord group where a lot of a lot of discourse, a lot of discord takes place. So yeah, and as Phil said on the website. Okay, Chuck has a couple of things.
Yeah, hey, before I get started, so Jim, on your image, if you put in the coordinates for the globular cluster on Aladdin Light, you can probably find out what galaxies those are.
Okay.
If that's
Mix Insight does that too.
Okay, all right. So what I was going to share with the group tonight is a project that I've been working on. Over the last year or two, I've been doing a lot of work on contact binaries, taking surveys, survey information that's in the AAVSO's international database, where there's been no observations, but just the original survey, and doing some dedicated imaging and time series photometry. What I'm sharing tonight is actually a particular project, but also what I'll be sharing with the National Science Olympiad this year. The astronomy section is doing stellar evolution and variability, and I was asked to speak on behalf of some of the work that I've been doing in photometry. So I'm doing some applied photometry as a topic. So this particular project is V404 Gemini. It's a contact binary. It's got a period of just about 8.5 hours that these two stars are orbiting each other around a common center of mass. And I just shared, the particulars of the observatory, which is remoted out in California with the plane wave telescope, the camera, the ZWO 2600, the Paramount mount. And in this case, I was taking 90-second V filter images and 75-second R. And over the course of 5 nights that you can see here, 1,223 observations. So the panels, as you read across, I've got just one image that shows the target, the comparison stars, the check star. And I won't go into all the details here. I just want to kind of skim the highlights, but happy to talk to anyone that's interested in doing photometry. I'd be more than happy to work with them. What you see in the next panel is the 5 nights I collected, and there was one night where I alternated. I'm sorry, previous slide. So I was going left to right. So the second panel here is the 5 nights where I collected, and there was one night where I just alternated the V and the R filters, and then one particular night in the bottom left down here. So you can see the two eclipses that occurred. First, you had the primary eclipse where the brighter star is being eclipsed, and then the second one is where the dimmer star was eclipsed. Based upon the 5 nights of collection, I was able to do a period analysis to determine, what was the period, and then produce a phase diagram and that's a composite of all 5 nights of the V filter. The next slide, if you want to go there, Victor. The first thing I looked at was what's called an observed minus calculated. Many of you have probably done this before, but for each one of the eclipse, I looked at what the published time that the eclipses should occur. I compared it to what I observed, and it was a very, very nice, very straight line where it was consistently about 70.8 minutes late compared to the original survey, which had been done back around the 2005 timeframe. So things have evolved with this system in the last 17 years. The next panel shows that night where I alternated. And so I could figure out a color index. And based upon the two filters and a color index, you can estimate what type of system you're looking at here. And that's the math that you see in the bottom left, which is this appears to be a G-type system similar to our sun. And then the final panel is what's in the database versus what I observed. And some things are very similar, like the magnitude range was pretty much dead on. The period was off a little bit by about 52 seconds. And over the course of 17 years, that could account for 70 minutes of being late today. And then, of course, I can now come up with an epic based upon the work that I've done and be able to predict future eclipse times, and then continue to follow up and see if the period is changing at all, because, as these systems continue to orbit each other, they're exchanging mass, they're in contact, and things are likely evolving over time. So anyways, I appreciate the opportunity to get to share some of it, and always
super cool.
happy to work with the team here too.
Super cool. Can you just explain for those who don't know what the R and the V filters are?
So sure, those are the Johnson-Cousins photometric filters. They are centered at a very specific wavelength within the visible band. The V is very close to the green area in the center, and the R is within the red, not quite into the infrared, but it's around I want to say around the 6,500 to 7,000. I've actually got that on another chart that I didn't include today. But taking narrow slices of the light coming in, again, you can look at what's the difference at the same point in time. And there's research that's been done across the spectrum of stars that, depending upon the filters, the standard filters, you can look at that difference, and then you can estimate what the effective temperature is of that particular star, which allows you to make a judgment in terms of what type of star it is.
Neat.
I have to assume you have connected with Dennis Conti.
Oh, yes. Yeah. Dennis. So I've worked with Dennis quite a bit on exoplanet work. And also now, we can do some of this work on eclipsing binaries, in Astro Image J as well, and upload these things to AAVSO.
Very cool.
Yeah.
Okay, I'm going to stop recording, and maybe we can just talk for a couple more minutes. We're